Okay, we're ready for our second talk this morning. So we have Brent Nelson, who's going to tell us about strong one-boundedness and graph products. I guess I'm going to go with this strongly one-boundedness.
Yeah. Okay, maybe a typo there. Yeah, thank you. Thanks to the organizers for inviting me to speak. So this is in collaboration with most of the audience. So my collaborators should feel welcome to provide commentary, but maybe not too welcome to provide commentary. And this is work that we did as part of an AIM Square at the American Institute of Math. So throughout, I'm gonna let G be a simple undirected graph. So in particular, I'm gonna not allow self-loops at vertices, and between two vertices, there's either 0 or 1 edges with no orientation. And then given a family of tracial von Neumann algebras indexed by this vertex set, I want to construct a larger von Neumann algebra using the data from this graph. They're tracial von Neumann algebras. Their graph product is, I'll denote it, I should maybe say graph product over G, because if you change the graph, you'll get a different algebra. Sometimes you see, well, we've adopted the following notation. So this is an algebra with several properties. So first, you have a trace-preserving inclusion of each of your vertex algebras into the larger thing. Next, then this is actually generated by all these individual algebras. Okay, and then the last two pieces of this definition are that the edges should determine the various relations amongst these algebras, the position they're sitting relative to each other in this larger algebra. So in particular, if you have an edge, say B and W, then we're going to demand that the copy of MV commutes with the copy of MW. And then otherwise, in the absence of an edge, then you want to assert that they're as far away from commuting as possible, namely, they should be freely independent. With respect to this tau G. And this I should specify is for V not equal to W. Okay, and so you can explicitly construct this thing. It's if you're familiar with the construction of the free product of von Neumann algebras, it sort of follows a similar story. You first talk about how to take a graph product of pointed Hilbert spaces by taking some large direct sums of tensor powers of the Hilbert spaces, and then you represent the von Neumann algebras on that larger space. And the story is similar here. It's just that these various relations from the edges are sort of determining which tensor factors you exclude from this big direct sum. So I won't get into the details. The important parts are these relations that you're able to witness here. Okay, and this construction I should mention is a bit more general than this here. I'm demanding that these are tracial von Neumann algebras, but one can do this for all states. Yes? Here I'm just demanding that they're in. Just that they're commuting. Yeah. Sure. Okay. Yes. The intersection is sort of scalars. Okay. Okay, good. So no. Sure. Yeah. Okay. Let me maybe give you some examples. This is all irrelevant to the talk, I'd say. So let's move on. So of course, if you assert that you have every single edge possible, then this is the dominating condition, and the resulting thing should just be the tensor product of these. Okay. Uh-huh. Okay. I will now. Thank you. Yeah, sure. Okay. Great. Very constructive. Let's move on. So let's say you don't have any edges whatsoever. Then, of course, this becomes the dominating relation, and you end up getting the free product with respect to these various traces. Okay. Now, beyond this, you can, with sort of lower level examples, you can still play games here. Let's say your graph is of this form, square. Maybe you label it 1, 2, 3, 4. And well, you can observe that since there's no edge between 1 and 4, then these algebras should be freely independent. Likewise, through and 3 should be freely independent. But also 1 and 4 are connected to the other ones, so they should commute. They should be tensor independent with the other copies. And so what you end up getting in this case is something like this. Of a tensor product of free products. So you can play sort of ad hoc games with these lower level examples, but you don't have to go too deep into examples of graphs to get something that we don't quite fully understand. The first one is maybe the 7-point graph. And so I'm going to make every edge adjacent to the ones next to it and the ones that are 2 over from it. So give me a minute to draw this. And well, okay, we don't really understand the isomorphism class of this thing. Okay. So in general, these things tend to be difficult to understand as long as the graph structure is somewhat interesting. Another nice feature of these, though, and this can occasionally be helpful to understanding what these look like, is that they admit nice amalgamated free product decompositions. So if you fix, say, a vertex in V, let me denote by B the ball of radius 1 centered at this point, so all the vertices connected to V naught and including V naught. And let me make S the sphere of radius 1, so that'll be the things that are precisely distance 1 from it. And then if I say denote the algebras generated by these vertices appearing in these sets, MB, MS, and then the complement of V naught. Then what ends up happening is the entire graph algebra splits as an amalgamated free product of these 2 things, which each contain a copy of this piece. So you get that MG is amalgamated free product. Okay, and if you're extremely lucky and this ends up being, say, like an atomic algebra or a finite dimensional thing, then the techniques by due to Ken Dykema can usually let you kind of suss out what this thing actually is. But often this is infinite dimensional, and so this only gets you so far. So okay, in the work with my collaborators, the question we're interested in is, when does strong one-boundedness show up in the context of these graph algebras? So when is MG strongly one-bounded? And well, I was hoping that I could just put Ben on the hook for defining this, but he managed to arrange for his talk to occur before mine. So now I feel obligated to give you a definition, and I've taken the liberty of writing the definition on the board ahead of time, but I'm a little worried this is going to be like opening the Ark of the Covenant in Indiana Jones. So if you're afraid of analysis, maybe you make peace with God now. So this is one bounded entropy. Yeah, okay, it's not so bad, right? So this is our microstate space. We're looking at matrices B, whose law with respect to the trace in the presence of some other thing, which I'm not going to talk too much about, gets you close to the target law that you're after. The target law being for these tuples, and this K epsilon is the epsilon packing number for these things. Okay, and then classical entropy theory tells you sort of what to do from here. You take a log and you normalize by the dimension of the space, and then you take all of these things to sort of collapse this to as tight a space as possible. Okay, and so strong one bounded. Well, okay, so the sort of remarkable thing about this, or the very nice property of this, is that it ends up not actually depending on these individual generators. It rather just depends on the von Neumann algebra that they generate. And yes, for the experts in the room, I'm taking a little bit of liberty with this definition, but and so we say M is strongly one bounded if this quantity is finite. Okay, and for the purposes of this talk, the only really way that you need to think about this is that what does it take for this to be finite? Well, then evidently these packing numbers aren't growing too fast as epsilon gets small. So you should think of that as just there's not that many microstates. Okay? This is a very rough understanding of it, but for the purposes of this talk, it's enough to get by. Okay? And the sort of critical thing is that, well, something for which this fails are free group factors. So in particular, this can distinguish you from free group factors. And using this and other properties, as we saw in Ben's talk, you can get a lot of mileage out of this quantity. Okay? So we want to understand when this happens for these graph algebras. Okay. So here's the theorem. There are 6 of us, so I'll just write a hexagon. Sorry, let mg tau g be a graph product of von Neumann algebra, where I'm just going to demand my vertex set is at least 2, so this doesn't become trivial. And the first case is, well, if all of these MVs are diffuse, and then we also say con-embeddable, then we know exactly when this is strongly one-bounded, and it's just precisely when the graph is connected or not. We say something slightly more general in the paper. We can also consider when they're not necessarily con-embeddable, but let me not delve into that universe too much. So then what ends up being the much more interesting situation is sort of not when they're diffuse, but when they're finite dimensional. And in this case, we don't have a full characterization about when strong one-boundedness occurs, but we do have a sufficient condition. So let me denote by A the unital star algebra generated by these finite dimensional algebras. Then what we're able to say is that Mg is strongly one-bounded if the first L2 Betty number of the star algebra is 0. And in fact, we conjecture that in this context, this ought to be an if and only if. We conjecture it in slightly more general context as well. But so what is this L2 Betty number? So these were first defined by Kahn and Schlichtenko using an L2 homology theory. But in practice and in the way that we use it, we invoke a different picture of this that's a cohomology theory that was established by Andreas Thom. So you can think of this condition as saying that, that all of the derivations on A that are valued in its associated coarse bimodule are approximately inner. Okay? And just to sort of give a sanity check for this about why this might be true, well, one reason why your derivations might be approximately inner or might generally be trivial is because you might have lots of relations, right? If the graph is sort of not sparse enough, this is demanding a lot of relations, and relations tend to kill derivations, make it very hard to define derivations when you have to respect a lot of relations. Okay, and well, those same relations are going to likewise crush down your microstate space. Okay, so that's not a proof, but these are at least sort of detecting the same sort of thing. Okay, so let me now tell you a little bit about the sketch of the proof of this, and then I'll kind of specialize here. But if there's any questions while I'm erasing, please fire away. Ben? Oh yeah, that's right. Yeah, this takes the value of it's valued in here, and yeah, when you're in the non-conembeddable realm, you're sitting in this situation. So, and I should say another motivation for considering this is that right now all of our examples are only taking the values of -infinity, 0, and +infinity. But there's nothing preventing anything from occurring in between these two values. So, one of our hopes was that maybe one of these graph algebras, maybe this 7-point guy, who knows, one of these things is going to actually have a one-bounded entropy that's strictly between 0 and infinity. That would be something we're very interested in. But correct, yeah. They're all clustered on those three values: -infinity, 0, and infinity. Not yet, I think. Not yet. Well, okay, sure. Talk to Ben. Right. So let me give you a sketch of the proof of 2. Sure. Yes. For example, if you know that M has property T, for example, this gives you nice upper bounds. But that's right. In terms of the things that we can compute it precisely. Exactly. Yes.
You do not know in the example to prove that the one-bound entropy is finite and circular.
Correct. Sure. So the first step of proving 2 is to show that nice microstates for, I should say, first let's fix a bunch of generating tuples For my vertex algebras, say in some NV, demand self-adjoint, I guess, generating tuple, and then I'm going to concatenate them all together to form a generating tuple for my graph algebra. Okay, and step one is to show that if you have what I'll refer vaguely to as nice microstates for the generating tuples on each individual vertex algebra, show that these give rise to, again, quote unquote, nice microstates for X using random matrix theory, more precisely using sort of strategic conjugations by uniformly random permutations. Okay, and this will be what I spend the rest of the talk, or most of the rest of the talk discussing, is exactly how the random matrix theory comes into play to do this, how you can use it to model this sort of relations that I'm demanding in the graph algebra. Okay, and here nice refers to a concept that we developed in this paper called algebraic sophicity and also Galois bounded. The idea is that you want microstates consisting of sequences of matrices whose entries are in algebraic integers. Okay, and a bit more precisely, you want them to be algebraic integers that lie over finite extensions, finite field extensions of the rationals where the index is uniformly bounded along your sequence. Why would you want such a thing? Well, the point is that for such matrices, this gives you control on how far the determinant or the product of the non-zero eigenvalues is from zero. It lets you sort of bound that away from zero. That'll be relevant in step two. Okay? And that's another reason why we have to consider permutations here rather than, say, conjugating by Haar unitaries, because the permutations will respect this delicate algebraic structure, whereas conjugating by a Haar unitary will completely eradicate that. And then the second step is basically then just apply a theorem of Dimas. Which says the following. So suppose the L2 Betti numbers satisfy the following formula. In our case, we're assuming this is zero, and this zeroth L2 Betti number becomes zero as soon as, say, your algebra is diffuse, which is again in our situation. So for us, this formula looks like 0 minus 0 plus 1. If you have this, and if a certain Fugolid-Cattison determinant is strictly positive, then you get strong one-boundedness. So if x trace tensor tau of log plus absolute value df of x strictly positive, then mg is strongly one-bounded. Okay, and so, well, you can see exactly how I'm using this hypothesis that my first L2 Betti number vanishes. It's to satisfy this condition here. And then step one is allowing us to witness this. So f here is some family of relations plus a few other polynomials coming from your tuple f. But the point is that if you have these nice microstates, the corresponding quantity along your microstate sequence will be uniformly bounded below. And because they're going to converge in distribution to your x, you'll get such a lower bound in the limit. Okay. And I should mention that Dimas result is more general than this. He doesn't demand that this is 1. If you call this alpha, then the conclusion under this is that you get something called being alpha bounded. And that's, okay. It says something about how the asymptotic behavior of this. But let me not go too far into that. Okay. So for us, then, the whole game is to establish just 1. Okay? And that's what I'll spend the rest of the talk discussing. Yes? What? What do you mean? Yes, correct. Yes. Another one? Oh, because yeah, sure, sure. Well, you don't know what dimension this is over, so. Yeah. Well, these are valued in the, you've taken like conjugate free difference quotients of your generators. Yeah, sure. Okay. Thank you. Okay, so before I get into like the random matrix models that allow you to do step one, let me maybe combinatorialize a bit better this graph product business. Call it G independence. So first, we say a tuple V1 through Vd of vertices is G reduced if whenever Vi equals Vj for I less than j, then there should exist some k in between them, so that Vi Vk fails to be an edge. Okay? So what is this getting at? Well, suppose I had some word of elements indexed by these vertices where each of my XVI is coming from the Vi vertex algebra. And if it were the case that, say, for simplicity, Vi and Vi plus 2 are equal, but Vi and Vi plus 1 did form an edge, well, then the relations in my graph algebra tell me that I can take this product and I can commute, well, either one of these past the other. Let's do the first one to the second. Vi plus 2. And so now I can just group them as a single factor coming from that same vertex algebra, and I've reduced the length of my word. Okay? So when I don't have this condition that there's something not connected to them in between them, then I'm able to reduce the word smaller and reduce the word and make it smaller. Okay? That's right. Yeah, this is for simplicity. Yeah. So I mean, there just needs to be something. But if everything in between was an edge, then I could commute past all of them to get it there and still reduce it. Okay. Well, so remember it's an undirected graph. So as soon as this is an edge, then the other one is an edge. And also since they're equal, I can swap out Vi plus Vi and Vi plus 2. So yeah, I'm hiding the symmetry, but it's there. Yeah. Okay. So then let's give like a combinatorial definition of this G independence. So let's say you have a non-commutative probability space. And G as before, a simple undirected graph. Then we say a family of subalgebras family of unital star subalgebras is G independent. Okay, I'm worried this is going to get me into trouble again, but you'll let me know. If one, they should commute with each other. Whenever V and W is an edge. And then two, this is supposed to be capturing the free independence aspect of this, but it only applies to these reduced words. So if V1 through VD and D is G reduced, and if AI belongs to AVI, and it's centered for each I from 1 to D, then we expect phi of their product to be 0. Okay. And so in particular in my graph product von Neumann algebra, the family of vertex algebras are G independent in the non-commutative probability space offered by their graph product. Okay. So finally, let me get to these random matrix models. So let's fix our graph. And then I have to, well, let me just write this. Let's consider the set S given by taking the complement of the edges inside of V times V. Okay. And for each V and V, let's define S sub V to be all the edges, say UW, or all the pairs UW in S, such that V is equal to U or V is equal to W. Okay, so all the pairs where V shows up as one of the entries. And because I've excluded self loops, that means that in the complement of this, I have the diagonal subset of pairs V comma V. So this will always at least contain one edge, namely V times VV. Okay, now the important properties of this, which I'll leave for you to convince yourself of, is that in particular, well, SV is non-empty, right? I just told you at least one element in it. And for different distinct vertices, this intersection is empty if and only if they form an edge. Okay. Well, anything in here, by definition, has to have V showing up in one of the coordinates and W showing up in one of the coordinates. And since they're different, that meant that it was not an edge. Okay, so now with these sets established, we're going to do a construction modeled after one developed by Charlesworth and Collins. From 21. So for each integer k, I'm going to look at a tensor product over the elements in SV. I'm using E, which is maybe dangerous because these are not edges, but they're not vertices, so non-edges, yeah. So I'm just taking a bunch of copies of the same matrix algebra tensored over this set. And I'm going to identify this inside of when I take a tensor product over the full set S. In the sort of canonical way induced by the inclusions of these sets. So I can identify this with let me write this down here. This is the same thing as so as algebras, those are isomorphic, and this thing sits naturally inside of here. Okay, so from now on, I'm just going to identify this copy, and let me even label this thing as boldface M SVK. Okay, and this over here I'll label as boldface SK. And well, the way you should visualize this is you should think of all of these tensor factors as a bunch of strings. Okay, and then when I have one of these subsets SV, the matrix elements are sort of supported on each one of these strings. So each one of these corresponds to a copy of the matrices. Then I'm taking a big tensor product like this. So, for example, I could have a subset that's supported on these strings. This somehow corresponds to one of these subsets. And then maybe I have a different one that's only supported on these strings, corresponding to a different choice of vertex. And the point is that because of this property over here, that the subsets intersect, or the subsets are disjoint exactly when I have an edge, what this tells me, or what this translates to algebraically, is that these subalgebras will commute if and only if these form an edge. Okay? And this is exactly the kind of relation we want them to have in our graph algebra. So already with this tensor product model, I'm encoding exactly one of the relations that I need, that edges should confer commutation. But then to turn this into something that can appropriately model this notion of G independence or my graph algebras, I need to inject some freeness into this. Okay? And so the idea is to use Voiculescu's ideas here that if you do hard unitaries that are freely or independent, they converge to freely independent things. Likewise, the analogs of this result, like Dudanica, that you have the same thing for random permutations. And then by conjugating by those, you can generate some freeness. Okay? So more precisely, let me say what we'll do. So let me now fix a bunch of random permutations. I'll call them sigma vk, v and v, k and k, k and n, be uniformly random, independent, uniformly random permutations, where I want each one of these to take values in this associated algebra, SVK. Okay? All right. So then the dream, the hope is that if you consider the families that you get then by conjugating by these random permutations, you would hope that these families, at least asymptotically, as you let k go to infinity, converge to a G-independent family. Okay? Notice by requiring that my permutation be isolated to this subalgebra, I'm not disturbing this commutation property. So I will have that always at every level. But what should hopefully be manifesting asymptotically is the freeness, and that should come from this conjugation by permutations. Okay? And to be precise, let me say exactly what I mean by asymptotically G-independent. Well, right, G-independence requires these two properties. I'm saying that we will always have the commutation by how things have been arranged. So the only thing I need to guarantee is that in the limit I get this kind of thing. So that is, so I hope these are asymptotically G-independent. That is, I want the limit as k goes to infinity, the normalized trace of, say, some conjugation P1k, P1V1k, minus the trace of the same thing. And the conjugation of VD, K star, PVD, K, minus its trace. I want this limit to be 0 whenever this is a G-reduced tuple of vertices, and these P's, PVI, K, belong to this algebra M, SVI, K, I from 1 to D, are uniformly bounded. Okay, yeah, Jorge. Well, okay, spoiler alert, it's not. I will correct for this in a minute. But yeah, let me talk a bit about the history here for why you might expect this. And you're sort of immediately seeing the issue, but we'll get everybody else caught up. So first, let me mention a result due to Nika from 93. Which is that this is true, or sorry, rather, that random permutations are asymptotically free. So the above is true for G, the graph with no edges. Yes? And then the other result that sparks hope is due to Ian and Benoit, where we stole this model from. Oh, with permission from Ian, right? Which is that this is true for Haar unitaries. for any graph G. Okay. So this is why you might expect this to be true, and you know, this is what we first attempted to do, but as we were muddling around in the computations, and by we, I mean David and Ian, they realized that, yeah, this is not quite the correct statement, and probably for the reasons that you're getting at. Rather, what we show is, instead of these things being asymptotically G-independent, we show they're asymptotically G-independent over the diagonal subalgebra. actual theorem is following. That V1 through VD, VG reduced. And let's let PIK, rather than demanding that it lives in this particular subalgebra, I want to look at it in the subalgebra where I allow coefficients in the diagonal algebra. Oh, I should, let me use this other board first to set some notation. I'm going to label the diagonal subalgebra as dk inside of this big ambient algebra. And then delta k will be the conditional expectation onto it. So I'm going to allow these PIKs to live in, let me just write this as the join of the diagonal algebra. And this algebra, I should say here, conjugate by my random permutation. Okay. And be uniformly bounded. Sup over I and k, their norms. It's finite. Then the actual limit we establish as k goes to infinity is that the 2 norm of delta k of P1 k minus delta k P1k square bracket here. That the 2 norm of this in limit is 0. And this holds almost surely. Well, we first check that it holds in probability, and then using concentration, we upgrade to almost surely in the standard way. Okay. And well, it seems like we lose because this is the thing that we needed to assert that we had G independence. Okay, but the counterpoint is, well, you know, this is deleting the diagonal of my elements P. So if I already deleted it in the first place, then I don't actually have to minus this delta. So if one has that, say, delta k p I k equals the trace of p I k times 1, or at least asymptotically, for every polynomial, then just by substituting in this into the asymptotic limit, I get exactly the G independence. Then we get G independence from the theorem. Okay, and in the particular example that we're interested in, we need to sort of apply this to an algebra generated by microstates for our vertex algebras. Okay, and in part 2 of the main theorem, the vertex algebras were just matrix algebras. So in fact, my microstates are just going to be constant matrices. Okay, and how can you achieve this for all polynomials in those things? for MV finite dimensional, use the following isomorphism that the n by n matrices I can view as a the group von Neumann algebra for Z mod NZ, okay, C to the n, semi-direct by Z mod NZ. And here the action is I'm viewing this thing as the dual of that thing and using the usual action, okay? And, well, if you write down what this thing actually is, it's just the span of words of the form UG V P, say for G and P, 0 to n. N minus 1, yes. Okay, and well, these things are sort of shifted off diagonal matrices, and you can check that all polynomials in these have diagonal 0 unless you're talking about the identity element. Okay, so we in fact get equality up here. Always, so we get a very strong result. Okay, but you can generalize this to other algebras when you can achieve this. And that gets into this notion of algebraic sophicity, which I do not have time to talk about. So that's all I wanted to say. Thank you very much for your attention.